Let me introduce Professor Dmitri Talapin. Professor Dmitri Talapin is an honest David Button Distinguished Service Professor in the Department of Chemistry, James Planck Institute, and Pritchard School of Molecular Engineering at the University of Chicago. And Professor Talapin received a number of prestigious awards, and he was elected a fellow of RSC in 2014 and served as an associate editor for Chemical Science. Okay, so please welcome Professor Talapin.
Thank you. Thank you. Let me share my screen.
Okay, thank you.
Can you hear me?
Yes, I can hear you well.
Okay. Now so thank you for the opportunity to present today, and I will be discussing novel approaches to solution synthesis of different technologically important semiconductor nanomaterials. And first, well, as a chemist, I think about nanomaterials as a pretty dramatic extension of the concept of macromolecules. We all used to and are very familiar with organic polymers, which used in so many applications, but I think over past 30 years, we have seen a dramatic expansion of this space of macromolecular objects into different families of inorganic nanomaterials, or inorganic solids. And now we can, in many cases, complement processability of polymers and their diversity, but with properties and applications more traditionally covered by solid-state materials. And today I will be talking about one particular subset of inorganic macromolecules, which are crystalline semiconductors built of hundreds to thousands atoms each, and they're mostly familiar under the name of quantum dots. So these nanocrystals of semiconductors can be represented by different semiconductor families. Probably we can separate this space and divide this space into three families, which historically the first was chalcogenides and cat selenide, zinc selenide, lead sulfide, and other materials that could be made with a very impressive degree of structural and compositional control. Later, this family was extended by synthesis of 3,5 semiconductors, and a big portion of my talk today will be related to 3,5 semiconductors, but also the latest addition to this family was lead halide perovskites. And all these materials have all these families differ in the type of chemical bonding. For example, lead halide perovskites are most labile, have most labile ionic bonding, while pnictides or 3,5 semiconductors are by far most difficult to synthesize, but it comes because of covalent bonding, but also it defines bond rigidity. And overall, the combination of properties of these materials translates into their practical applications. So many of quantum dots are now either used or extensively researched for applications that span displays. One of the probably greatest achievements of nanoscience so far are QLED displays, pioneered by, or developed, commercialized by Samsung. And it is viewed as just the first generation technologies, because we now have a roadmap towards second and third generation where quantum dots will not only absorb light and emit light as they do in current QLED TVs, but will be also engaged in much more complex operations, more traditional for bulk or epitaxial semiconductors, such as absorption of light, separation of electron-hole pairs, charge transport and carrier collection and so on. And this, there are many reasons to believe, and pretty reliable experimental proof of concept data that such materials can be used in electrically injection light emitting devices, or LEDs, and infrared detectors, circuits, transistors, photovoltaic devices, and so on. Now, today I will be talking about different ideas that we have been researching recently towards how to make these materials even better and push them beyond their current state of the art. And my presentation will be divided in three sections. First, I will talk about how far can we push atomic precision for synthesis of nanoscale materials. Then we will talk about some general concepts behind what can and what cannot be synthesized in solution, and then keep with me, and you will see what will be the last section of this talk. But first, let's see. I already draw the connection between nanocrystals, or quantum dots in particular, and macromolecules, or polymers. And in many ways, intellectually, we are following the same footsteps that polymer community has been dealing with over several decades. And one of the most fundamental questions and challenges in the in the field of polymer synthesis was, how can we improve synthesis, synthetic control over polymers? Can we grow a polymer chain with atomic precision? And it's formulated in that community in terms of polydispersity indices, PDIs, and traditionally, in the early generation of synthetic approaches, there was no good way to control chain lengths, and it was pretty much controlled kinetically. But the development of advanced polymerization techniques such as leaving radical polymerization and others enabled to bring PDI very close to unity. We really now can control polymers, and it opened up a whole scope of applications, including block copolymers and many others. But to start, let me give you a brief video of synthesis of typical synthesis of quantum dots. So in a quite typical prep, we have several chemicals mixed together, and they react. And during these few seconds, as you see it, two very important processes happen in the reaction mixture. The first is the nucleation. So the molecules nucleate and form crystals, and then these crystals grow. And depending on what type of chemicals we use in these flasks, we can control the growth to make spherical particles or shaped control particles and so on. And there was a lot of work along these lines accomplished by the community. Now, if we want to bring it to the next level, we need to understand and improve control for both steps. First, nucleation. So the nucleation, let's consider classical nucleation theory. So it's the idea is that in order to nucleate, the system must climb the nucleation barriers, activation barriers, and grow to the size of the critical nucleus. And it's typically, well, at least in the classical realization of this nucleation approach, the idea was that the nucleus forms uniform or nearly spherical, or as close to spherical as possible. But it turned out that there is a lot of dynamics in the pre-nucleation stage, and along certain trajectories, the pre-nucleation clusters experience large shape fluctuations. And if they develop shape anisotropy, then something interesting can happen. So instead of growing layer after layer by nucleating new layers at the relatively large extended surfaces of these pre-nucleation clusters, they can break into the growth of a two-dimensional structures. And by growing thin, but by one-dimensional nucleation of thin stripes at the surfaces of narrow facets of this dynamic pre-nucleation cluster. And this idea has been first introduced in 2017 by David Norris group in Switzerland and ETH, but later we realized that it can be something much more broad in general. So in principle, we can redefine the concept of crystal nucleation as trajectories on the potential energy surface defined in the coordinates of free energy and critical dimension of the crystal and volume of the crystal. And the system can climb the full classical nucleation theory nucleation barrier and fall into a stable and nucleate a stable crystal. But also there are valleys, side valleys, where that will lead to metastable compounds. But each of these valleys will lead to atomically precise structures or structures with atomically precise critical dimension. And that free energy surface actually links together clusters, wires, two-dimensional structures called platelets. And if we can control trajectories on this potential energy surface, we can direct the system into one of these metastable structures, and it will work for all crystals. We don't need to have something like graphene or molybdenum disulfide where chemical bonding is special, such that crystal is forced to grow, let's say, in 2 dimensions. In this case, we can apply it to crystals with cubic crystal structures, such as zinc selenide or cadmium selenide. And by navigating solution, by controlling temperature and reagents into one of these side valleys, we can grow ensembles of particles where every particle will have exactly the same thickness. For example, like in these platelets, and we have a full flask of them, so we can scale it as much as we want, and then we can separate or individual or not separate, we can grow selectively populations of particles with different thicknesses. So it works surprisingly well and can be controlled with very impressive degree of precision. And these are all ensemble spectra. So these materials show incredibly narrow emission. But that's what we can achieve by controlling nucleation. But if we want to turn it into a methodology for making arbitrary complex structures, we need to link it or couple it to atomically precise growth. So in order to achieve atomically precise growth, we can take an inspiration from the method of atomic layer deposition, or ALD, which is used at every semiconductor fab for growing conformal coatings on silicon wafers in the CMOS process. So, for example, the key idea here is that the growth of a new phase, like in this case, aluminum oxide phase, is divided into 2 half reactions where each half reaction is self-limiting. So it means that the surface, when you expose surface of silicon wafer to excess of trimethyl aluminum, you will grow a single layer of aluminum, alkyl aluminum fragments, and the reaction will stop there. Second layer will not grow. And then you can do second half reaction and keep going and growing conformally 1 layer at a time. What we proposed to do for colloidal science was to implement self-limiting pairs of self-limiting half reactions for synthesis of colloidal nanostructures. And the idea is to grow layer after layer by what we called colloidal atomic layer deposition. And that allowed us, for example, by completing 8 layers of colloidal ALD, we can put 8 layers on each side of the structure. And again, if we have atomic precision after the nucleation stage and couple it to this atomically precise growth, we can grow pretty complex structures. Like in this case, we have started with central plates and then grew 1 layer of cadmium sulfide and 3 layers of cadmium zinc sulfide barrier layers and another interfacial layer of cadmium sulfide, and finished it with quantum another side, quantum wells of cadmium selenide. So it's pretty close to molecular beam epitaxy, but now in solution. And we can do it in parallel on huge number of nanostructures in solution by doing colloidal atomic layer deposition, and we do not introduce inhomogeneous broadening. When we claim that we grow one layer at a time, we did a lot of experimental studies, spectroscopic studies, to validate that it is very close to reality. So, for example, after that many layers of colloidal ALD, the ensemble emission spectrum will have pretty good Lorentzian line shape and extremely narrow line widths. And ultimately, it brings us one step closer to our goal that we can define as digital nanomaterials, where we can connect physical concepts such as band gap engineering, interfacial engineering, strain engineering, and map them on experimental observables that we need for device for optimization of device operations. And we can close the loop between theory and experiment, where we really know what we grow. Overall, the scope of types of structures that can be grown is pretty large, but in terms of applications, I'm sure it's also very broad scope of applications can be accessed by this chemical methodology. But to start somewhere, we realized that quantum wells, these structures are electronically closely related to quantum wells. They're 2D electronic systems, and as you probably know, quantum wells are pretty familiar materials for lasing applications. And it turned out that our colloidal two-dimensional quantum wells are amazing optical gain media with very low lasing thresholds and very large model gains that can be, again, processed by solution chemistry. And when coupled to resonators or cavities with very small mode volumes, we can make efficient lasers with low laser thresholds and pretty good device reliability. But it's just probably a first step. So with designing such a complex structures, we can make materials. We can go after much more complex physics, such as superfluorescence and coupling between multiple chromophores and many other effects that have been previously realized in structures grown by molecular beam epitaxy, but now we can do it by more like traditional chemistry in solution, in scalable way, in a very cost-efficient way, and implement them for much broader scope of technologies. Okay, with this, I would like to kind of finish the part of discussion on colloidal ALD and precision, and with a word of caution. I probably painted a very optimistic picture that we can control synthesis of nanocrystals down to atomic precision and so on and so on. And yes, we can do it for a very small subset of materials that can be efficiently nucleated and grown at temperatures around like 300 degrees Celsius or so. Because in that reaction, in that video that I have shown you a few minutes ago, the flask here the solution in the flask was preheated to 370 degrees Celsius. And that's arguably the highest temperature we can really push the solvents to. At the same time, it's still not enough to meet the conditions that have been previously proven to be optimal for growing of materials like gallium arsenide or gallium nitride. So if we look at the parameter space accessible for solution chemistry and compare it to parameters used for CVD growth of gallium arsenide or gallium nitride, we will find that we are pretty far away from where we want to be. And in other words, the current synthetic methodology works really well for materials that crystallize below 400 degrees Celsius. But if we try to apply solution chemistry to grow, for example, gallium arsenide quantum dots, we are out of luck, and that has been proven by about 30 years of unsuccessful attempts to make these materials by solution chemistry. So the real problem, if we think deep into why we cannot grow some of materials by solution chemistry, comes not from our inability of making chemical bonds, such as gallium arsenic bond in solution, or gallium nitrogen bond, but actually opposite, from inability to break these bonds. Because for growing crystals, especially in 2D and 3D cases, the chemical bonding must be reversible. We need to be able to repair occasional misbound fragments in order to grow crystalline material. And if we don't have reversibility, we will run into a problem. And that can be demonstrated on the example. If you look at the bond dissociation energy of materials that we can easily synthesize by solution chemistry, such as cadmium selenide or zinc selenide examples I've shown previously, and compare it to the materials that we cannot synthesize by solution chemistry or couldn't after several decades of efforts, we will find that like gallium arsenide has much stronger bonding as well as gallium nitride. So in traditional MB or CVD chemistry, this problem is addressed by going to high temperatures. We use KBT thermal energy in the system to break chemical bonds and establish reversibility. So overall, it kind of creates an interesting situation where we have two ecosystems for chemical synthesis. On one hand, we have solution chemistry, where we rarely go above 200 Celsius, and I'm talking about such fields as organic chemistry, organometallic chemistry, and so on. On the other hand, we have equally powerful ecosystem of solid-state synthesis of semiconductor technologies, where we very rarely go below 500 degrees Celsius. So they are pretty different ecosystems, I would say. And we've been recently thinking, how can we bridge, if we can bridge these two universes and enable efficient knowledge transfer and be able to do chemistry, especially colloidal chemistry, at temperatures above 400 degrees Celsius. And with this idea in mind, we started looking for alternatives to traditional organic solvents and organic or chemistries and chemicals used for colloidal synthesis, and arrived to the idea of that maybe we can use molten salts as solvents for doing colloidal synthesis. The only problem was that at that time, there was no such thing as a colloidal solution, a colloidal dispersion in molten inorganic salt. And these are first examples of, in that case, those were platinum nanoparticles that have been dispersed in the eutectic mixture of aluminum chloride, sodium chloride, potassium chloride. And actually, this eutectic has a melting point of 97 degrees Celsius. So we're not talking about some outrageously high temperatures to work with. So you can do clever chemistries there and phase transfers and so on. And we've been lucky to identify that nanoparticles can relatively easily form colloidal dispersions in these molten salts. And I was asking myself around that time, how comes that it has not been discovered like 100 years ago? And the only rational explanation I could come up with was that the very fact of colloidal stability of particles in molten salts goes against every bit of common sense as we know it. Now, to remind you what defines colloidal stability. So in order to form a stable colloidal solution, we need to have net repulsive pair potentials. When two particles come together, they need to repel each other, and that will prevent aggregation. So there are two ways to impart colloidal stability. One is steric stabilization, when we attach to the surface molecules with large number of configurational degrees of freedom, and they define so-called steric stabilization, or impart osmotic forces and into acting as a repulsive part of pair potentials. If we work in polarizable, if we put particles in polarizable media, we typically rely on so-called electrostatic stabilization, where we attach charged groups to the particle surfaces, and they impart electrostatic repulsion. Now, in molten salts, we don't have anything that looks like polymer brushes to install steric repulsion, and it's a very polarizable medium, so we need to rely on analysis previously developed for colloidal stability in polar solvents, and that typically looks at this class of theories known as Dirac-Landau-Fareway-Overbeck analysis and its extensions typically compares van der Waals attraction to electrostatic double-layer repulsion. But the problem with molten salt is that it has such a high ionic strength or such a high polarizability that the electric field cannot extend beyond like 1 or 2 interatomic distances. So the Debye screening length is on the order of 1 angstrom, which doesn't make sense. Pretty much, this analysis doesn't make sense and at these length scales. And in other words, the double layer repulsion will be always inferior to van der Waals attraction in every models that we dealt with. Or on the other hand, we found that these colloids do exist, and we can prove it by a variety of experimental methods. So in order to understand it better, we did a lot of theoretical analysis, we did Monte Carlo molecular dynamics simulations, we did hard X-ray pair distribution function analysis, or so-called double differential pair distribution function analysis to understand what's going on. And it looks like in molten salts, we switched to completely different regime of electrostatic interactions in solutions. So typically, when we have dilute electrolytes or solutions with relatively large Debye screening lengths, well, the electric field decays exponentially into solution, and that is described by Debye-Huckel regime. And that's where all traditional colloids operate. But if we go into very high concentration electrolytes, the electric field is not decaying exponentially into solution, but it starts oscillating and propagating further beyond the Debye screening lengths. It is a regime that is not accounted by the Debye-Huckel. It's not accounted by DLVO series. It's a new regime where the interactions extend about an order of magnitude beyond the Debye lengths, and that these interactions are responsible for colloidal stability. Now in molten salts, and in many ways molten salts are very rich environments where we can control loose basicity, loose acidity, they can be loose neutral, they can be reduced, oxidized, and understanding ionic equilibrium in molten salts turned out to be a very interesting and important part of this exploration. But of course, kind of we are practical people, and for us the question was, in addition to all these amazing intellectual developments, can we do something that we couldn't do without using molten salts? And I'm sure that many materials can be made, but we had to start somewhere. And as a starting point for this exploration, we decided to focus on a very important challenge in the field of colloidal quantum dots, which is a synthesis of 3-5 quantum dots beyond indium phosphide, indium arsenide, and indium antimonide. The reason why we focused on these materials, because 3-5s are pretty much the most successful semiconductor family if we talk exclusively about performance. Like if you look at the famous chart of record solar efficiency solar cells for different types of semiconductors, the upper third of this chart is exclusively 3-5 world, because 3-5 semiconductors allows you to very precisely engineer electronic structure and lattice parameters, and you can make multiple junction multiple junction devices, and as a result, the fastest transistors, the most powerful lasers, the most efficient solar cells, they are all made out of 3-5 semiconductors. And we really want to be able to build these materials, replicate these materials by scalable solution methods. So what we learned over many years of exploration, that we now have amazing methodology for indium phosphide and indium arsenide synthesis, but we couldn't make gallium-containing materials for a number of reasons. First, gallium is very oxophilic. Second, gallium-3 is too strong loose acid, and it does some side reactions at high temperatures, such as CH or beta hydride elimination, CH bond activations. So we had severe problems to synthesize gallium-containing quantum dots using traditional organic chemistry. But in molten salts, all these problems kind of magically disappeared, and we could go to higher temperatures. We could go to pure oxygen-free environments, pure CH-free environments, and in first generation of methods, we started with indium phosphide, for example, quantum dots, and did cation exchange to make indium gallium phosphide. And we could fully cover the space from pure indium phosphide to gallium phosphide. And the reason why these materials are interesting and important, because traditional QLED TVs are all serviced by indium phosphide quantum dots. And indium gallium phosphide is more stable, thermodynamically more stable phase than indium phosphide. So, and it better lattice match to zinc sulfide. So that was a motivation for us to go after better understanding of indium gallium phosphide core zinc sulfide shell quantum dots, and we found that these materials can be pretty well engineered and optimized, so we can make indium gallium phosphide quantum dots covering a very broad range of indium to gallium compositions with quantum yields accessing like 80% or so, so that is pretty much on par with current indium phosphide quantum dots. Another very interesting point about indium gallium phosphide is that as we move through the composition, we go through very interesting change in the band diagram, in the band structure. Like indium phosphide is a direct gap semiconductor, but gallium phosphide is an indirect gap semiconductor. And as a result, we switch at some point from direct to indirect as we change indium to gallium ratio. And that's exactly what we see experimentally, like in the indium phosphide reach case up to about 65% indium, we have a pretty bright emitting, well-behaving quantum dots where we can use amount of indium introduced or gallium introduced into the quantum dot to control the band gap. But as soon as we cross into the indirect gap, the PL, photoluminescence disappears, and that adds to very important, allows us to make a very important fundamental conclusion that has been debated in our community for many years. Like, is crystal momentum a good quantum number for quantum dots in this size regime? And actually, yes, it looks like it is an important and conserved quantity in the quantum dots, in the quantum dot regime. But indium gallium phosphide is just the first example. Equally, with comparable degree of control, we can make indium gallium arsenide, we can make indium gallium antimonide type structures. And overall, like in semiconductor engineering, especially in the space of 3-5 materials, we often rely on diagrams like this, where band gap or electronic structure is related to the lattice constants, and it allows us to map and start and interface and couple of properties of different 3-5 semiconductors. And it also allows us, I want to use this plot to kind of put you in the context of what we can and what we cannot do. So by traditional solution synthesis using organic solvents, we could make indium phosphide, indium arsenide, and indium antimonide quantum dots. And with a little effort, we may be able to access mixed nictide compositions. But judged by, again, several decades of hard work using organic solvents, I strongly believe, and in our most recent data, that you need molten salts to make these other compositions, and we have demonstrated the possibility of making these materials, and all this space can be covered using molten salt synthesis. So I have many reasons to believe, and many experimental data to justify these claims that molten salts open up a much broader space for colloidal synthesis. And altogether, it kind of helps us to further advance technological progress for quantum dots as a field. As I already mentioned to you, quantum QLED displays is just the first step. These materials are used or researched for many applications, from infrared detectors, cameras, machine vision applications, different energy applications, from solar cells to solar concentrators. And I think by now, thanks to the work of a large community, both in academia and in industry, there is a pretty wide agreement that quantum dots provide a very competitive and versatile platform for optoelectronic devices, such as light-emitting devices, infrared detectors, field effect transistors, and so on. And to a large degree, state of the art at the level of individual devices, we as community have proven that performance of individual devices can be very competitive and in many cases superior to any other materials that can be processed non-epitaxially by solution-based techniques, for example. But it's not actually the place where we want to be. Our ultimate goal is to bring this individual devices proof of concept examples to the systems level. For example, single LED pixel is good, but 100 million individually switchable LED pixels in form of 8K TV is much more important, much more valuable product, same as focal plane arrays and so on. And that brings me to the last section of my presentation, where I will, at some point, we realized that there was a missing link in order to move from individual devices to the systems. We need to have more tools and more versatile tools for patterning, for placement, for positioning, and it relates to the previous presentation by Professor Merkin, but we approach this problem slightly differently. We introduce the concept of direct optical lithography of functional inorganic nanomaterials, or Dolphin. That's where Dolphin comes from. And the idea is that by traditional patterning of colloidal nanoparticles has been accomplished by transfer printing or inkjet printing, and those are good techniques. But if you want to push resolution, or especially if you want to push throughput, you need to look at you can greatly benefit by switching to or borrowing ideas from traditional photolithography, where you can define literally billions of circuit elements in a single lithography step. That's what kind of is behind our traditional semiconductor technology. And traditional photolithography uses organic photoresists as a sacrificial pattern defining medium, and that upon exposure changes solubility, and then you can open windows in photoresist, and then you can do pattern transfer. And for additive pattern transfer, it turned out that one of important limitations of traditional photoresists is capillary effects and swelling of the resist in presence of solvents that we use for quantum dots. So we and others tried to implement traditional photolithography to do well-defined and well-controlled patterning of quantum dots, and we had very limited success. So instead, we suggested that we can engineer surfaces of quantum dots in such a way that they will be act as their own photoresists. So all we need to do is to implement photochemical activities to the surface ligands of quantum dots and prepare quantum dots with photochemically active ligands, and then we can pattern them directly, and they pretty much bring all the resolution and throughput of traditional photolithography to the field of colloidal nanomaterials, and that can be applied to quantum dots, to many other nanoparticles too. And there are many approaches. Our historically first approach for engineering photochemically active ligands was using photoacid generators, or PAGs, that allowed us to change solubility of particles in the exposed versus unexposed areas. But it's just one approach. You can use photo decomposition of heterocyclic compounds. You can use all kinds of other chemistries that are tailored to certain wavelengths and serve different purposes. For example, if you want to push resolution, you need to design ligands that will be photochemically active in deep UV. And then you can make really small sub-micron patterns. You can use eye line molecules sensitive to the I line or 365 nanometer light to make it more gentle and minimize damage of quantum dots. Or if you want to push cost as much as possible, you can switch to 4 or 5 nanometer and use salt gel compounds, and then it becomes much more cost efficient. But overall, this Dolphin, this engineering of surface, using surface photochemically active surface ligands allows you to pattern metals, oxides, semiconductors, perovskites, pretty much every material that can be made in form of nanoparticles can be patterned with exposure dose very comparable to the exposure dose of commercial photoresists and same resolution. So you can do it for example, for patterning meta surfaces with oxide, using oxide nanoparticles, so you can control phase of light. You can also pattern active micro LED or LED pixels, and that is important. Like here again, as a word of caution, we need to be careful understanding what where the challenges are. If we talk about large displays, where the subpixels are about 100 nanometer by 100 micron by 20 micron, I believe those pixels can be ultimately inkjet printed. But if we talk about micro displays for IR and VR applications and many other modern technologies, where pixels are sub 10 micron, or subpixels are about smaller than 10 microns, it's highly unlikely that we will ever be able to reliably inkjet print those pixels. So we need to look for approaches like Dolphin, and there are many different chemistries that we and most recently others tried for Dolphin and its variations. And this is one of the examples where we showed the first patterning of LEDs and showed that you can pattern LED pixels, for example. And overall, it builds the entire what we call Dolphin ecosystem, where we can make positive patterns, negative patterns. We can push resolution. We can down to pretty impressive, like sub 100 nanometer. We can do three-dimensional patterns. We can do device patterning. So it's a huge ecosystem, and definitely I invite everybody interested to join this race, because I'm sure there are many opportunities in this space and at the translation, at the point of translation from fundamental science to technologies. And with that, my time is up. I want to bring you to the most important slide of this presentation. I'm incredibly thankful and appreciative to the great team of students and postdocs who worked with me over the years at the University of Chicago. Many of them are now professors. Some are professors at KAIST, PostTech, and other famous Korean universities. And also I want to thank funding agencies who made all this work possible. And thank you for your kind attention. Thank you.
Thank you very much for the very impressive and interesting talk, Professor Talapin. And now time is open for question. Then also you can refer the Q&A. Let me read the first question. Thank you for impressive talk. The cation exchange was used for the synthesis of quad shell structure or bimetallic semiconductor. Did they have exactly same stoichiometric composition? I wonder how to control the same ratio for all of the nanoparticles.
Well, this is a beauty of colloidal chemistry. So when you have a colloidal solution, so particles do not aggregate, then every particle has the same boundary conditions, and there is a driving force. The extent of ionic exchange reaction is very similar to each other, because each particle is separated. And you would not be able to accomplish this if particles would aggregate it, because definitely if ions are diffusing from outside, particles that are sitting inside aggregate experiencing a very different concentration profile at its surface than particles sitting at the surface of the aggregate. So that's where you need colloidal stability. And overall, there will be, of course, there will be some variation. I don't want to say that we have like exactly same composition. So there will be a little variation, but surprisingly, it works quite well. So the ensemble line width of these colloids is not bad. It's slightly inferior to the best indium phosphide samples, but not much.
Okay. All right, thank you. And next question, I would like to ask the production scale of the molten salt-based synthetic method. Is it possible to implement mass production like the conventional method?
I think yes. And it's a lot of kind of discussions these days in our lab, and we do experiments, we do first attempts to scale up. We can go to very high concentrations, and so you won't need to use like very large volumes of molten salts. So maybe to make a long story short, I think it's possible. And I don't see major obstacles, but at the same time, of course, the future will show. So we need to work with industry more closely on this particular goal of scale up.
Okay, thank you. The last question, which is a more important factor between reaction time and temperature for quantum dot synthesis? Do you think, is it possible that the cation exchange with other ions can obtain high entropy alloy semiconductor quantum dot?
Yes, I really believe at the moment that sky is the limit. Yes, we can do a lot of complex. We now have up to 5 element 3-5 phases, so we can mix pnictides. We can mix gallium, aluminum, indium in these structures. So we didn't think about this from the point of high entropy alloy structures, but yes, I think it's pretty close to high entropy alloy systems. And in terms of what is more important, temperature or time, well, these are two parameters, convoluted parameters. So it's if you go to high temperature and short time, it probably allows you to better establish a core shell structures or gradient inside quantum dots, individual quantum dots. If you go to operate at relatively low temperature but go over longer time, in that case we had better alloying and more uniform compositions. At least at the moment, that's what our experimental data suggest. And but yeah, you need to optimize for each system separately.
Okay, so thank you for your kind answer. And I would like to thank the Professor Talapin for the excellent contribution to our symposium. Thank you very much.
Thank you.